The universe is balanced on a razor's edge. If the fundamental forces were off by a tiny fraction, stars wouldn't burn, galaxies couldn't form. That's the mystery of cosmic fine-tuning. It's a puzzle at the heart of cosmology. You'll see the staggering number of coincidences that make our reality possible. The expansion rate of space had to be perfect, and a specific nuclear resonance inside stars that makes our existence a statistical miracle. So many precise adjustments were needed to build a cosmos from nothing. You can think of these forces as ingredients. Each one has a specific strength, a precise number. We call these the fundamental constants. They're like fixed settings, dials on reality. They govern everything, from a planet's orbit to a heartbeat. And here's the first mystery. Our theories don't predict these values. We can't calculate why gravity has the strength it does, or why the nuclear force has its exact number. We just go out, measure, and write down what we find. The shock is when you look closely, they aren't random. They are, with unbelievable precision, exactly the values you need to build a complex cosmos. Take the strong nuclear force, the glue inside an atom's core. If it were just a few percent stronger, protons would bind too fiercely. Hydrogen would be unstable. All the hydrogen in the early universe would have fused. Almost instantly, without hydrogen, there are no stars. Stars like our sun burn hydrogen. No stars means no light, no heat, no production of heavier elements. The stuff of planets and people. But if the strong force were a few percent weaker, it couldn't hold nuclei together at all. Not a single element beyond hydrogen would be stable. The universe would be a thin soup. Isolated protons, no complex chemistry, no foundation for anything we see. That the strong force sits in this narrow zone, it's not a minor detail. It's a foundational requirement for a universe that contains anything more than featureless gas. This precise calibration repeats across all the fundamental forces and constants. The strength of gravity, the charge of an electron, the mass of a quark. Each one appears perfectly tuned, as if chosen from infinite possibilities, to allow for galaxies, stars, planets, and life. This arrangement feels too specific. For a random accident, it suggests a cosmos that was, from its first moments, curiously arranged, precisely arranged. For the possibility of structure, the recipe didn't call for a pinch of this or a dash of that. It demanded perfection. There's this one number, the cosmological constant. It's a term in Einstein's equations, an energy that's just part of empty space. We connect it now to dark energy, the thing making the universe expand faster. But its value is so precise. It's set so perfectly it doesn't make ordinary sense. Think of the universe right at the start. That initial explosion, the Big Bang, had an immense outward force. And then there was the collective gravity of all the matter and energy, pulling everything back inward toward a collapse. The cosmological constant is a repulsive pressure. It pushes space itself apart. The difference between these two forces, the push and the pull, had to be almost exactly zero. The accuracy is almost impossible to grasp. If that repulsive push had been stronger, even by a tiny, tiny fraction, the universe would have expanded too fast. No galaxy could form, no star. Gravity would be powerless. Everything would dilute into a cold, empty void before any structure could begin. And if the constant had been slightly weaker, gravity would have won. Immediately, the universe would have expanded for just a moment, then reversed, collapsed back in a big crunch. The whole story would have lasted just an instant. For the universe we see to exist stable and long-lived, that balance had to be perfect. Not for 1,000,000 years, for over 13 billion years. Steven Weinberg called this the cosmological constant problem. He said it might be the most glaring case of fine-tuning in all of physics. It's like balancing a sharp pencil perfectly on its tip. Not for a second, but for the entire age of the cosmos. That impossible stability is what let gravity do its slow work. It gave time for tiny quantum ripples in the early universe to grow. drawn together by gravity's whisper. They became the seeds for everything: galaxies, clusters, the whole cosmic web we see. Without that one number being set with such impossible care, none of this would be here. The universe had time from that balance, but it needed a blueprint. The early cosmos wasn't perfectly smooth. We see that in the cosmic microwave background. It's the afterglow, a map of the infant universe, and it shows a pattern. Tiny variations in density, ripples frozen in time. Those were the seeds for everything. But the seeds had to be the perfect size. Their strength was another dial set with impossible care. The density differences were minuscule, about 1 part in 100,000. That's the difference between a smooth pond and one with ripples the height of a sheet of paper. If that dial had been turned down, if the ripples were fainter, gravity would have had nothing to grab. Matter would have spread out forever, never coalescing, a vast, dark emptiness, a void with no story. Turn the dial the other way, though, make the ripples stronger. Then gravity becomes a monster. Not gentle nudges over eons, you get violent, immediate collapse. Matter slams together, forming enormous black holes catastrophically early. A cosmos of voracious singularities, swallowing everything before a single star could ignite. No galaxies, no spiral arms, just a chaotic graveyard. Somehow, the universe got it exactly right. Those 1 in 100,000 ripples were the Goldilocks condition, strong enough to give gravity a starting point, gentle enough to allow a slow, graceful dance. Over hundreds of millions of years, those slightly denser patches pulled in more gas. They grew, they merged, they became the first protogalaxies. The gentle nudges became great cosmic cities of stars. All from a whisper. This precise setting wasn't just about making stuff. It was about making the right kind of stuff. A universe that collapses into black holes is sterile. A universe that never clumps is barren. Our universe found the narrow path between them. It wrote a recipe for complexity. But even with the perfect conditions and the perfect blueprint, you still need the right raw materials. The building blocks themselves had to be forged under another set of perfectly tuned rules. The cosmic clock started in the first second. The temperature was unimaginable, a seething ocean of particles. Protons and neutrons just formed were bouncing in that frantic heat. This was the era of Big Bang Nucleosynthesis, the universe's first act of creation. For a brief window, about 3 minutes, conditions were just right for nuclear fusion, but not inside stars, those didn't exist yet. It was happening everywhere at once. The whole universe was a single forge. Protons, which are hydrogen nuclei, began to collide with neutrons. They stuck together. They formed deuterium, a heavy hydrogen. And then these deuterium nuclei fused further. They built the next element in line, helium. This was a delicate race against time. The universe was expanding and cooling very rapidly. If it expanded too slowly, the fusion would continue unchecked. Every proton would find a partner. All the hydrogen would become helium right then. The future would have no stellar fuel. The first stars would have nothing to burn. But if the universe expanded too quickly, the opposite would happen. The particles would fly apart before they could link up. The cosmos would remain almost pure hydrogen. A universe of only hydrogen can't build planets. You can't have complex chemistry. You need that initial batch of helium forged in the Big Bang to seed the future. It's that helium that helps stars later burn hotter. That lets them create heavier elements. The outcome of this race hinged on 2 balanced factors. The first was the strength of the weak nuclear force. This force governs how protons and neutrons transform into each other. It set the initial ratio in that primordial soup. Get that ratio wrong, and the recipe is ruined from the start. The second factor was the expansion rate of the universe itself during those first minutes. It had to provide just enough time for the right amount of fusion. Then it had to shut the process down. Not a moment too soon, not a moment too late. The result of this precise nuclear alchemy. When the forge cooled, the universe was left with a specific mix. about 75% hydrogen, 25% helium, and trace amounts of lithium. This is the foundational chemistry for everything to come. It's the precise elemental inheritance the first gas clouds would have. The universe was setting its initial conditions. It created the raw fuel and the essential lighter elements, but this fuel was still simple. It was scattered across a darkening cosmos. To build the complex world we see, these simple ingredients needed to be gathered. They needed to be compressed and ignited. They needed a factory far more powerful than the Big Bang's brief flash. They needed the enduring fires of the first stars. The universe had its first fuel, but to build anything complex, you needed more than just ingredients. You needed the right kind of glue, and that glue comes from a relationship inside the atom. It's the ratio of the proton's mass to the electron's mass. A proton is about 1,836 times heavier than an electron. That number isn't random. It's another one of those precise settings. A dial that had to be set exactly where it is for chemistry to even exist. Think of an atom like a tiny solar system. You have the heavy protons and neutrons at the center, the nucleus. And then you have these incredibly light electrons whirling around it in a cloud. That mass difference is everything. Because the electron is so much lighter, it can be shared. It can be traded between atoms. That sharing is the basis of every chemical bond. It's how you get water, how you get DNA, the molecules that make up a leaf or a mountain. Now imagine turning that dial. If the proton were only, say, 10 times heavier than the electron, then the electron would be a significant part of the atom's mass. It would orbit very close to the nucleus, held in a tight, rigid grip. Atoms would become isolated islands, unwilling to share their electrons. Chemical bonds would be feeble or impossible. The universe would be a collection of simple, inert gases, no molecules, no liquids or solids, no planets, just diffuse clouds. No chemistry means no possibility for life. Turn the dial the other way. Make the proton vastly heavier, maybe 10,000 times the mass of the electron. Now the electron is vanishingly light by comparison. Its cloud would be enormous, loosely bound. Atoms would be gigantic and extremely unstable. They'd constantly interact, merging and breaking apart chaotically. Orderly structures could never form. No crystals, no stable molecules. The cosmos would be a reactive, sloshing sea of unpredictable matter. Our ratio 1,836 sits perfectly between these two dead ends. It gives electrons just the right behavior. They're light enough to be mobile, to form the bonds that build complexity, but they're still firmly attached to their nuclei. Creating stable, predictable atoms. That stability allows for specific, crucial elements. Carbon, with its perfect ability to form 4 strong bonds. The backbone of organic chemistry. It relies on this exact atomic architecture. If the mass ratio were off, carbon itself might be unstable, or unable to form the intricate chains and rings essential for life. So this number does more than define an atom. It builds a bridge. From the silent quantum world, it constructs the rules for all tangible things. The dust between stars, the rocks of a planet, the chemistry in a cell. All of it depends on that original, perfect setting. The microscopic handshake between proton and electron echoes upward, shaping the very galaxies we see. But for those galaxies to light up, the fuel within them needed to ignite, and that ignition, the birth of a star, required its own set of miraculously tuned conditions. Gravity is the weakest force, by a huge amount. It's trillions of times weaker than the force that holds an atom together. But it's the one that writes the story of the cosmos. It's the quiet pull that builds everything. It gathers the gas, it shapes the galaxies, it sets the orbits, and its strength it's on a knife's edge. If you turn that dial even a little, everything changes. Make it stronger, just slightly. Then a star is a balance, fusion pushing out, gravity crushing in. Strengthen gravity, you tighten the vice. The star burns its fuel with a desperate intensity. A star like our Sun, meant to last 10 billion years, would blaze through its life in a few million. It would flare and die before planets could even form. The universe would be filled with these brief, brilliant flashes. Then darkness, no long-term stability. No places where life could ever begin. Now turn the dial the other way, weaker gravity. Then the inward crush becomes a feeble nudge. It can't gather things. Those ripples in the early gas, the seeds of all structure, they just dissipate. Particles drift apart forever. No clouds collapse, no stars ignite. The cosmos stays a vast, thin, eternal haze. A universe without islands, just a featureless sea. Somehow, gravity found the middle. Its weakness is its strength. It's just strong enough to slowly, patiently gather the scattered matter over hundreds of millions of years. To pull gas into clouds, compress them until fusion sparks. And yet, it's just weak enough to let those stars burn with a steady flame for billions of years. That long, stable lifetime, it's not a luxury, it's a necessity. Because a star is a forge, it cooks hydrogen into heavier elements, but this takes time, immense time. It takes a billion years to build carbon, billions more for oxygen, silicon, iron. If stars died quickly, they'd only scatter the lightest stuff back. The periodic table would be barren. Our gravity gave stars the gift of time, time to simmer. Time to build complexity, atom by atom. And then, at the end, through gentle winds or violent explosions, they scatter their forged riches. That stellar dust becomes the raw material. For rocky planets, for oceans, for us. But that scattering, that distribution, it's its own story. A story of another profound balance. That dust from old stars, it doesn't just stay dust. It gathers. Out in the dark, between stars, these huge clouds start to form, nurseries, giant molecular clouds, so big they could swallow whole solar systems. That's the raw material, the potential. But for a star to actually come out of that, another set of perfect conditions has to line up. The cloud starts to collapse under its own weight. Gravity pulls it in, but as the gas compresses, it heats up. Heat means pressure, and that pressure pushes back against gravity. That's the fight. The battle that defines a star being born. For the collapse to keep going, the cloud has to lose that heat. It has to cool. And here, the tiny world decides everything. The cloud cools through atomic transitions. Atoms and molecules colliding in that dense gas, they can radiate energy away as infrared light. That process, ruled by quantum mechanics, has a specific efficiency. A rate, and that rate had to be perfect. If atomic physics made that cooling less efficient, the cloud would never shed enough heat. Internal pressure would win. The collapse would stop. The cloud would just sit there, a warm, stable blob, a failed star. The universe would be full of these dark, massive things, but no light. But if the cooling was too efficient, the opposite disaster. The cloud loses heat too fast. Without that internal pressure to push back, gravity goes wild. The cloud doesn't gently contract into one star. It shatters. It fragments into countless tiny, cold clumps, each one too small to ever ignite fusion. You'd get a galaxy full of brown dwarfs, dark Jupiter-sized objects, a cosmos in perpetual twilight without a single real sun. Our universe found the narrow path. The cooling rate, set by atomic constants, matched the gravitational binding energy almost exactly. It let the cloud fragment, yes, but into chunks of just the right mass. Large enough for gravity to crush their cores to millions of degrees. To start fusion, that's how one giant cloud can give birth to a whole cluster of stars. Each one a potential sun. But ignition is just the start. For a star to be more than a simple hydrogen-burning lamp, it has to build. It has to do stellar alchemy. And that needs a miracle inside the furnace. The star fuses hydrogen into helium. But to make carbon the essential element for life, it has to fuse 3 helium nuclei together. That's a notoriously difficult process. 3 particles have to collide at almost the same instant. In the chaos of a stellar core, the odds are astronomically low. so low that for decades, physicists wondered how any carbon existed at all. The answer is a resonance, a precise, matching frequency in the nucleus of carbon-12. When the combined energy of 3 helium nuclei hits exactly the right value, the carbon nucleus doesn't just form, it sings. It accepts the energy with a kind of joyful ease. This resonance is like a secret doorway, held open just for this reaction, and it's exquisitely tuned. The energy level of this carbon resonance is almost exactly the combined energy of 3 helium nuclei at stellar core temperatures. If it were just a fraction of a percent higher or lower, the reaction would crawl. Stars would produce almost no carbon. They'd burn helium into heavier elements inefficiently or not at all. The universe would be carbon-poor, and a carbon-poor universe is a silent one. No chemistry of life, no rocky planets, just helium-burning stars that leave behind ash, not a legacy. This resonance wasn't predicted, it was discovered, and when astrophysicists like Fred Hoyle saw it, he reportedly said it was as if the laws of physics had looked ahead. They'd arranged the nuclear forces to specifically enable carbon production, to make stars not just sources of light, but factories for complexity. Through this perfectly tuned doorway, carbon floods out. It becomes the backbone for further fusion, creating oxygen, nitrogen, all the elements of life. And when that star eventually dies, in a gentle planetary nebula or a violent supernova, it scatters this forged wealth back into the void. That enriched gas becomes the next generation of clouds, planets, possibilities. The star's work is done. It has translated the fine-tuning of fundamental constants into tangible substance. But for that substance to find a home, to assemble into worlds, the story needs one final, delicate stage of cosmic construction. That forged carbon, scattered into the void, needed a stable home. And that stability starts with hydrogen, a proton with an electron around it. But for hydrogen to be everywhere, another setting had to be perfect: the mass difference between a proton and a neutron. In a nucleus, they are bound together. They seem almost the same, but they aren't. A neutron is heavier, just a little bit heavier, about 1/10 of 1%. That tiny difference, it's not a detail, it's a rule. It decides what matter can be. Because of that extra weight, a free neutron is unstable. On its own, it decays. In about 15 minutes, it turns into a proton, an electron, and a neutrino. That decay is everything. It's why the universe isn't just neutrons. Now, imagine changing that setting. Make the neutron a fraction lighter, so light it matches the proton or even falls below it. Then the neutron is stable, it doesn't decay. In the first seconds of the Big Bang, when everything was forming from that quark soup, the balance would tip. With stable free neutrons, they wouldn't become protons. The early universe would fill with neutrons. They'd grab electrons fast, making a dense, neutral fluid. Normal atoms with their balanced nuclei couldn't form. Stars would still come together, but they'd be strange, ultra-dense things from the start. The cosmos might be full of neutron stars right away, dark, with almost no chemistry. This universe of galaxies and gas clouds, it wouldn't exist. Turn the dial the other way, make the neutron even heavier. Then the instability reverses. Now the proton becomes unstable. A proton could just decay into a neutron, and that would be a catastrophe. The building blocks of atoms would disappear. Hydrogen, the most common element, wouldn't last. Every atom's core would be under threat, dissolving. No stable matter could form. The universe would be fleeting, chaotic, unable to hold anything together. Our reality is here because the neutron's mass is on that razor's edge. Just heavy enough to decay when it's free, which makes the proton the stable cornerstone. But just light enough that inside a nucleus held by the strong force, it becomes stable. That perfect balance let the Big Bang make the right mix of protons and neutrons. It gave us a universe flooded with stable hydrogen, the fuel for stars. It let atomic nuclei with both protons and neutrons last for billions of years. That 1/10 of 1% margin wrote the first rule. It guaranteed a universe of light-lasting atoms. not a dark sea of neutrons, not a dissolving mist of decaying protons. From that foundational stability, gravity could do its work, pulling those stable hydrogen atoms together into the first glowing structures in the dark. Stable atoms gathered in the dark, but they didn't form random piles. They built galaxies, those spinning islands of stars. Their spiral arms, their existence, depend on something hidden. A form of matter that doesn't shine, doesn't collide. We call it dark matter. Without it, galaxies wouldn't exist. After the Big Bang, ordinary matter was under pressure. It was a hot plasma, pushed around by the energy of light. It couldn't clump. Those tiny ripples, the seeds for everything, couldn't grow fast enough in ordinary matter alone. The universe would have stayed a smooth haze, but dark matter is different. It doesn't feel the electromagnetic force. Light passes right through, so it wasn't pushed by that early radiation. When the universe was a bright fog, dark matter was already collapsing, forming vast, invisible wells, halos, in places where the initial ripples were stronger. These halos became skeletons, the gravitational anchor. Then the universe expanded and cooled. Ordinary matter could finally combine into neutral atoms. And it felt that steady pull. It flowed into those dark matter valleys. That's how structure was built. The invisible scaffold first, then the luminous city of stars on top. But dark matter itself had to have just the right properties. Another case of fine-tuning. If the particles moved too fast, were too hot, they would have had too much energy. They wouldn't be captured by those early gravitational whispers. They'd stream freely, smooth out the ripples. No dense halos would form. The cosmic web would be faint. On the other hand, if dark matter interacted too strongly with itself, or with light, it would have behaved like ordinary matter. It would have radiated, clumped into different shapes, altered the pattern we see in the cosmic microwave background. We don't see that alteration. The evidence says dark matter is cold. Collisionless, it moves slowly. Particles pass right through each other. That lets it form stable, smooth halos. Halos that can gently hold onto gas. This just right nature created stable gravitational potentials. Cosmic bowls, deep and calm. Hydrogen and helium gas could settle there. Pool, cool, condense. Only in these protected environments could the gas become dense enough, cool enough, to finally fragment and ignite into the first stars. Those first points of light did more than illuminate the dark ages. They began to transform the early universe. Their fierce radiation started to reheat the cosmic gas. Their deaths seeded it with the first heavy elements, setting the stage for everything after. The galaxy became a cradle, but for life to arise inside one, that galaxy and its star would need to be in a special place. All this precise tuning, from the nuclear forces to the neutron's mass, it creates a puzzle. How did a universe, starting from what we think of as chaos, get everything so exactly right? For many, the answer is in an event so brief it's almost not an event at all. A theoretical epoch called cosmic inflation. Picture the universe in its first moments, smaller than an atom. And it was filled with this peculiar high-energy field. This field had a property. It caused space to expand not steadily but exponentially, faster than light. In a span of time almost too short to conceive a tiny fraction of a second, the universe ballooned. By a factor of trillions upon trillions. This wasn't normal expansion. This was a stretching of reality itself, on a scale that's hard to even imagine. That sudden growth acts like a reset button. It explains several fine-tuned features at once. First, the flatness. Think of a balloon's surface. Blow it up to the size of the Earth, and any tiny wrinkle becomes imperceptible. Your patch feels flat. Inflation did that to the entire cosmos. It stretched any initial curvature so immensely that our observable universe appears geometrically flat. That solves the mystery of that perfect initial expansion rate. Second, the uniformity. The cosmic microwave background, that baby picture, is almost the same temperature everywhere we look. How did regions on opposite sides of the sky, which could never have communicated, come to such perfect agreement? Because before inflation, they were neighbors, part of one tiny, connected region. Inflation flung them apart to become the distant horizons we see, but they carried that shared, uniform temperature with them. And third, the seeds, the beautiful part. Inflation didn't create a perfectly smooth universe. At the quantum level, there are always tiny fluctuations. As space expanded exponentially, it stretched these quantum jitters from the microscopic to the cosmic. It imprinted them as minute differences in density across the vast new universe. Those became the 1 in 100,000 ripples, the precise blueprint for all future galaxies. So inflation didn't just explain uniformity. It explained the specific, perfect pattern of non-uniformity we need. It seems like a masterstroke, a single brief event that sets all the dials. It paints inflation as the grand tuner, but this leads to a deeper question. Does cosmic inflation solve the fine-tuning problem, or just move it? For inflation to work as described, the energy field that drove it had to have its own exquisitely tuned properties. It needed just the right potential energy shape to start the runaway expansion, and then a mechanism to decay gracefully, to stop inflation at exactly the right moment, and convert that energy into the hot plasma of the Big Bang. If it ended too quickly, the universe wouldn't be smoothed enough. If it never ended, we'd have an empty, eternally inflating void. The theory itself requires precise initial conditions. So we're in a curious loop. We invoke inflation to explain the fine-tuning of the cosmos, only to find the inflation we need is itself a finely tuned mechanism. That realization opens a door to a staggering possibility. Perhaps the tuning we see isn't a one-time miracle in a single universe, but an inevitable statistical outcome. Across a vast, perhaps infinite, ensemble of realities. So there's this idea, the Anthropic Principle. It comes in two forms, one is straightforward, the other is more speculative. The weak version just says we observe a universe that's compatible with our existence, because we're here to observe it. If it weren't fine-tuned for stars and galaxies, we wouldn't be here to notice. Our presence is a filter on what we can see. We're not observing from the outside, we're a product of it, looking from within. That's a selection effect. It doesn't explain why the tuning exists. It just notes our observation isn't a random sample. We are, by necessity, in the part of reality that allows observers. Then there's the strong version. That suggests the universe must have properties that allow conscious life to arise. It moves from a statement about our observation to a statement about the laws themselves. That they are somehow constrained to produce observers. That's where it gets deep, where many feel a line is crossed from physics into philosophy. The physicist Brandon Carter coined the term in the 70s. He framed it as a necessary correction. We can't ignore that our location in the universe, in time and space, is privileged. We exist after billions of years of stellar evolution, on a planet around a stable star, in a galaxy that formed. Any theory that doesn't account for this position might be missing context. There's a famous analogy, often attributed to Douglas Adams. Imagine a puddle waking up. It looks at the hole it sits in. It notices how perfectly the hole fits its shape. The contours match exactly. The puddle might think, this hole is designed for me. What it fails to consider is that it shaped itself to the hole. The puddle is a product of its environment. Its observation is a selection effect. It couldn't observe any hole that didn't fit. In this view, we are the puddle. The universe is the hole. The constants seem perfectly shaped for us because we molded ourselves to them through evolution. The Anthropic Principle, especially the weak form, is not an explanation. It's a framing device. It reminds us that our data point this one universe comes with a massive bias. We are the observers that the universe allowed. But this framing leads to a next question. If our existence selects for this kind of universe, could there be other universes we are not observing? Universes where the constants are different, where the puddle never formed. The Anthropic Principle by itself feels incomplete. It describes the frame of the puzzle, but not the picture within. To find an answer, we're pushed to consider a possibility that stretches beyond a single reality. That selection effect, the puddle fitting its hole, it's a real constraint. But it opens up something huge. If we're here, then the universe had to allow it. So what was the step that let matter exist at all? Because at the start, there was almost nothing. Or really, there were equal parts of something and its perfect opposite. The fifth fine-tuned number. It's the ratio, matter to antimatter. Every fundamental particle has a mirror. An antiparticle, same mass, opposite charge, and when they meet they vanish into pure energy, annihilation. Our best theories say the Big Bang should have made matter and antimatter in perfect balance. A symmetrical beginning, and if that symmetry held, everything ends right there. Every particle finds its twin, they annihilate. The whole universe becomes a bath of light. Just radiation, no atoms, no stars, no galaxies, an eternal featureless glow. But that's not what happened. We're here, made of matter, in a universe of galaxies made of matter. Something broke that symmetry, and it didn't break by much. A hair, about 1 part in a billion. For every 1 billion particles of antimatter, there were 1 billion and 1 of matter. That's the imbalance. That tiny preference, 1 in a billion, that's why anything substantial exists. After the Great Annihilation, that one leftover particle in every billion was all that remained. Everything, every atom in every star, every galaxy, every one of us, it's all built from that slim surplus, that microscopic residue. The process is called baryogenesis. And for it to happen, the laws of physics had to allow certain conditions to be violated. Just enough. Normally we expect symmetries, charge, parity, time. But in the early universe's heat, these symmetries had to break. Particles and antiparticles had to behave in subtly different ways, decay at slightly different rates, interact with fields in a non-identical manner. This violation couldn't be too strong, or it distorts the cosmos another way, and it couldn't be absent, or we get total annihilation. It had to be precise, enough to produce that 1 part in a billion excess. Think of a vast, cosmic coin toss at the dawn of time. The coin was perfectly balanced, expected to land equal heads and tails. But the very act of the toss, the conditions of the early universe, gave the coin an imperceptible bias, a weighting so slight you'd never see it in one flip. But this was the ultimate game of chance. Trillions upon trillions of flips everywhere, and that tiny bias over quintillions of trials produced a statistical surplus. Barely they're leaning toward heads. That leaning is everything we are. So the existence of galaxies isn't just about gravity having something to clump. It's about there being something to clump in the first place. Without that one extra particle of matter in a billion, gravity has nothing to work with. Space is empty. The cosmic microwave background would be the only relic, a brief, brilliant flash of mutual destruction. When we look out at the vast structures in the night sky, we're seeing the consequence of a number. A ratio set in the first fractions of a second. A preference so slight it defies our intuition for balance, yet so consequential it wrote the entire material story of the cosmos. It turned a potential universe of light into a universe of things. But with the stage set, and the players present, how did they come together to build not just any structures, but the specific, beautiful architecture we see? The 1 in a billion surplus left us with a cosmos made of matter. But then, why did that matter follow these specific rules, the ones that allow for life? There's an answer that comes from a pretty staggering idea. The idea that our universe isn't alone, that it's just one out of a huge number, maybe an infinite number of other universes. And each one has its own unique set of physical laws. That's the multiverse. You can think of it as a kind of landscape, an immense landscape of possibilities. Not of physical terrain, but of different stable states for the fundamental forces, different sets of constants. In one region, gravity is so strong stars form and burn out in an instant. In another, the nuclear forces are too weak to ever bind an atom. Most of these places would be barren, dark, silent, But if the array is truly infinite, then every possible combination has to exist somewhere. So from this view, our universe isn't fine-tuned for life. It's just the one universe from an immense ensemble that accidentally got the numbers right. The one where the constants landed in that very narrow window that allows for galaxies and stars, and eventually observers. There are mechanisms for this in our most ambitious theories. Eternal inflation, for instance. It suggests the rapid expansion of space in our early universe isn't a one-time event. It's a perpetual process. Bubbles of space, each with different properties, continuously pinch off from an eternally inflating background. And each bubble is its own separate universe. Then there's string theory, which tries to unify all forces. It proposes a landscape of possible solutions, maybe 10 to the 500 different stable configurations. And each one corresponds to a different universe with different physics. The metaphor is a cosmic lottery. The odds of any single ticket, of any single universe having the perfect combination, are astronomically small. But if the lottery has an infinite number of tickets, a winner isn't just possible. It's inevitable, and we are that winner. We find ourselves in a universe that seems impossibly special, not because it was designed, but because we couldn't find ourselves anywhere else. This is where the Anthropic Principle finds its home. It's the ultimate selection effect, and this idea offers a kind of statistical relief. It takes the mystery of fine-tuning and dissolves it into a matter of probability across a vast sample size. The universe isn't tuned. It's simply one possibility that worked. But this solution comes with its own profound challenges. The biggest one is testability. By definition, these other universes would be causally disconnected from our own. We can't observe them. We can't measure them or interact with them. Any evidence would have to be indirect, maybe imprinted on the cosmic microwave background from a collision in the distant past. So far, no such evidence has been found. And that leads many scientists to argue that the multiverse, while it might be a fascinating mathematical consequence of some theories, currently sits in the realm of metaphysics. It's more of a philosophical proposition than an empirical one. It also prompts a deeper question. If we accept an infinite multiverse, where everything that can happen does happen somewhere, does it diminish the quest for a single, elegant theory of everything for our own cosmos? Does it make our particular story less meaningful? The Multiverse Hypothesis doesn't close the book on fine-tuning. Instead, it opens a new chapter, one that forces us to confront the limits of our scientific inquiry, and to consider what kind of explanations we're actually looking for. But the multiverse can feel untestable. There are other roads, paths in cosmology that try to solve this from inside one universe. One idea is to question the force that builds galaxies. What if gravity doesn't work the way we think on cosmic scales? That's modified Newtonian dynamics. MOND. It starts with an observation. The outer stars in spiral galaxies rotate too fast. By Newton and Einstein, with the visible mass, those stars should be flung out. They aren't, they stay in orbit. The usual answer is dark matter, an invisible halo. MOND says something else. Instead of adding matter, we change the law of gravity itself. At very low accelerations, like out in the galactic edges, there, gravity gets a little stronger, just enough to hold those fast stars, no dark matter needed. If MOND is right, it removes a big piece of fine-tuning. The need for dark matter with its specific cold properties is gone. The fine-tuning of its density becomes an illusion. It's not a dial that was set. It's a sign our equations are wrong. The universe's structure would come from a revised law, but MOND has struggles. It has a hard time with galaxy clusters. The cosmic microwave background, it needs tweaks. It's a minority view, but an important one. It's a classic instinct. When the universe seems to need too many perfect coincidences, maybe we have the rules wrong. An even more radical shift asks a different question. What if the laws of physics aren't the starting point? What if they emerge, like wetness or temperature? Properties from countless simpler parts. Some theories say space and time, even the constants, aren't primary. They're the outcome of a vast underlying network. A quantum information network. A cosmic computation at the deepest level. In this picture, the constants aren't chosen, they settle. They're stable states a self-organizing system falls into. The universe finds its balance, like an ecosystem. The fine-tuning for stars and galaxies would be no more mysterious than a puddle fitting its hole. It's inevitable from the system's dynamics. The constants have these values because only these values allow a coherent reality at our scale. Other combinations might be possible underneath, but they wouldn't form a universe we could recognize. These emergent law theories are speculative, deep in theoretical physics, but they share a hopeful core. They suggest the cosmos might have a self-solving elegance. The balance we see isn't a pre-programmed input. It's the output of a deeper, maybe simpler, process. A process that leads to complexity. This keeps a single, elegant explanation alive. We might not need an infinity of universes. We might just need to dig deeper into this one, to find the source code our reality runs on. Each path, modified gravity, emergent laws faces huge hurdles. They aren't the consensus, but they are vital. They remind us fine-tuning isn't an answer, it's a question, a challenge to our understanding, and the history of science is written by those who rephrase the question. Who looked at the same mysterious numbers and asked not why they are perfect, but whether our ideal of perfection is the illusion. Dark matter and dark energy. They are these two huge unknowns, but they're not just mysteries, they feel like bookends. They hold up the whole story, and their roles, they don't seem accidental. They feel scheduled, essential. Dark matter built the structure, dark energy is setting the stage, and the timing between them, that's what matters. Dark matter was the architect. The unseen one. In the beginning, ordinary matter was trapped. It was this hot plasma tied to light. The light kept pushing it around, smoothing everything out. Gravity alone couldn't pull it together, not fast enough. But dark matter. It didn't feel that light pressure, it only felt gravity, so it could start collapsing right away. It formed these vast, invisible halos, long before any stars. Those halos became deep, calm wells, gravitational pits, and that's where the ordinary matter could finally flow. Settle, condense, but it had to be a specific kind of dark matter. It had to be cold. The particles had to move slowly. If they moved too fast, if it was hot dark matter, they would have streamed away. Washed out the seeds, the cosmic web would be a ghost, nothing dense, and it had to barely interact with itself with light. Almost not at all. If it interacted strongly, it would have heated up. Resisted collapse. Just like ordinary matter, so its nature cold, nearly collisionless. That's what made the perfect scaffold. Stable. It could hold the luminous universe without getting in the way. We see the evidence for this in the cosmic microwave background. Those tiny temperature fluctuations, they're a fingerprint, and they tell us dark matter was already working, shaping where everything would go, but doing it silently, without disturbing the early plasma. It was this patient, invisible hand. It laid the foundation for every galaxy. Then, for billions of years, the universe just coasted. Structure grew inside those dark halos. Stars were born, they lived and died, enriching everything. But there was this other force waiting, dark energy. Think of it as a property of empty space itself. A gentle repulsion. For most of history, it was negligible. The gravity of all the matter, dark and ordinary, that was dominant. That's what let galaxies form, let clusters assemble, let the whole cosmic tapestry weave itself. But as the universe expanded, matter thinned out. Its gravitational grip weakened, and then, at a specific point, about 5 billion years ago, the balance tipped. Dark energy's constant push became the dominant force. The expansion started to accelerate. The value of dark energy is the most precisely tuned number we know. It's incredibly small, but not zero. If it were zero, the expansion would just keep slowing. Never reverse, a cold but maybe connected future. If it were large and positive, Acceleration would have started right after the Big Bang. No galaxies, no stars, just a runaway emptiness. If it were negative, space itself would have a crushing tension. The universe would have recollapsed. Long before life, instead its value is just enough. It lay dormant for over 9 billion years. It gave the universe that long, quiet epoch, the time it needed to build complexity. It let gravity have all that time to sculpt galaxies, forge heavy elements, set planetary systems in motion. Only now, in these later chapters, does it step forward. To dictate the future, it suggests a timeline, one of astonishing precision. A long, fertile period for construction, then a transition into a different era. One that might lead to a cold, isolated fate. But only after the work was done, after building observers was complete. So together, they're not just placeholders for what we don't know. Dark matter and dark energy. They look like calibrated components in a universe that seems engineered for a journey that needed a beginning, a middle, and a very specific kind of end. To make this moment possible, that balance between dark matter and dark energy, it all comes back to a beginning, a first cause, and that beginning came from a place we can hardly imagine. The quantum world. That's the sixth finely tuned parameter. It's the energy scale of cosmic inflation, the number that decided how strong the seeds for all structure would be. We talk about those ripples, the blueprint for galaxies, but they had to come from somewhere. They weren't just there. They came from quantum uncertainty. In the very first instant of inflation, the universe was ruled by one field, the inflaton field. And like any quantum field, it wasn't perfectly still. It jittered. It had these tiny, unavoidable fluctuations, particles and energy popping in and out of existence, on a scale trillions of times smaller than an atom. Then inflation did something. It stretched space itself faster than light. And as it stretched, it took those tiny quantum jitters and blew them up. It magnified them, from the subatomic all the way to the cosmic scale. It froze them into the fabric of the expanding universe as slight differences in density. Those became the 1 in 100,000 variations we see in the cosmic microwave background. The same variations gravity later used to build everything we see. But for this to work, the energy of that inflaton field had to be set just right, with incredible precision. Around 10 to the 16 gigaelectronvolts. That's a number with 16 zeros. An almost unimaginable energy, a quintillion times more powerful than the collisions in our biggest particle accelerators. This energy scale is the dial for the strength of the seeds. You turn it up, you make inflation more energetic. Then those quantum fluctuations get stretched into enormous wrinkles. The density differences become huge. So when gravity takes over, it doesn't gently gather gas. It collapses it catastrophically. The universe would be filled with primordial black holes from the very start. A cosmos of monstrous singularities, swallowing any chance for orderly galaxies to form. Then you turn the dial down, you lower the energy of inflation. Then the quantum ripples are too faint. They get stretched into a nearly smooth canvas. The density differences are minuscule, whispers too quiet for gravity to hear. Matter never clumps enough. Stars never ignite. The universe just stays a vast, dark, eternal haze, a void with no story. Somehow, the energy was set exactly in that narrow middle. It produced fluctuations of just the right amplitude, strong enough to give gravity a starting point, gentle enough to allow for a slow, graceful construction over billions of years. This is a profound connection. It links the ghostly, probabilistic rules of the quantum world to the grand architecture of the cosmos. A random dice roll on the smallest possible scale, amplified into the destiny of galaxies. The microscopic and the macroscopic aren't separate. They're woven together in that first instant. The quantum fluctuation wrote the first draft of reality. And the energy of inflation was the hand that guided the pen, making sure the story wasn't a violent scribble or a blank page, but something legible. Something we're still learning to read. The universe needed that blueprint from the quantum jitters, but a blueprint is a plan. To build a cosmos from it, you need time. A very specific sequence, each event perfectly timed, like acts in a play where the curtain rises and falls at exactly the right moment. The first act after inflation was a hot, dense fog. A plasma of particles and light, constantly scattering. This went on for nearly 400,000 years. Then the universe expanded. It cooled enough for a fundamental shift. Electrons were captured by atomic nuclei. That's recombination. For the first time, neutral atoms formed, mostly hydrogen and helium, and when that happened, the light was set free. It had been trapped, bouncing off charged particles. Now it streamed out in every direction. That flash is what we see as the cosmic microwave background. That first light carries the map of the early ripples, but the timing was critical. If recombination happened earlier while the universe was hotter, the atoms might not have been stable. The light would have scattered again, erasing the clear snapshot. If it happened much later, the universe would have been more diffuse. The pattern on the light would be fainter. Harder to read. We needed that clear, sharp picture at just that moment. To preserve the blueprint, with atoms formed and light set free, the universe entered its second act. The Dark Ages, a period of profound quiet. No stars, no galaxies, just vast, cooling clouds of neutral hydrogen gas, slowly settling into the gravitational wells carved by dark matter. This epoch of darkness was essential. It was the time gravity needed to work undisturbed. Without the disruptive pressure from early starlight, gravity could pull matter together gently. Those tiny density differences began to grow. For hundreds of millions of years in the silent dark, the architecture of the future was being assembled. The Dark Ages provided the necessary pause, an incubation period, then, in the darkness, a spark. The third act begins with the first stars. In the densest knots of gas at the hearts of dark matter halos, gravity finally overcame pressure. The cores ignited with nuclear fusion. The first stars were born. They were not like our sun. They were behemoths, many times more massive, burning hot and fast. Their birth ended the Dark Ages. They flooded the cosmos with the first starlight in over 100 million years. The cosmic dawn, but these stars did more. Their intense ultraviolet radiation began to smash apart the surrounding neutral hydrogen, stripping away electrons. That process is reionization. Slowly, over hundreds of millions of years, these first stars burned bubbles of ionized plasma into the cosmic fog. The reionization epoch cleared the final haze, making the universe transparent to ultraviolet light, setting the stage for the light from all future stars to travel freely. This entire sequence, recombination, the Dark Ages, first light, reionization, each stage depended on the precise conditions set by the one before. If the Dark Ages had been shorter, stars would have formed before gravity had properly gathered the gas, resulting in a sparse universe. If reionization happened too violently or too slowly, it could have disrupted the formation of the next generation of stars. Stars like our Sun. The timeline feels orchestrated, a delicate chain of cause and effect, where the timing of each transition was as crucial as the physical constants. It built a universe not of instant brilliance, but of patient, layered construction. A universe that took its time to get the light just right. The universe had all that timing. But it still needed the right ingredients. It needed the building blocks, and that required a miracle inside the first stars, a precise nuclear resonance. The story of carbon starts with a prediction. In the 1950s, Fred Hoyle had a puzzle. The universe was full of carbon. Carbon is essential for life, for planets, for chemistry. But how did stars make it? The known path was a bottleneck. Stars fuse hydrogen into helium, then later they fuse helium. But to make carbon, you need to fuse 3 helium nuclei. 3 particles, all with positive charge, trying to collide at once, in the chaos of a star's core. The odds seemed tiny. The process should be incredibly inefficient, but the carbon was everywhere. Hoyle reasoned backward. Since carbon is abundant, the process must be efficient. For it to be efficient, the carbon-12 nucleus must have a specific property: a resonant energy state, a welcoming frequency. When the combined energy of 3 colliding helium nuclei hits exactly that frequency, the new carbon nucleus forms with ease. Like a lock clicking open, Hoyle calculated what that energy level had to be. He told nuclear experimentalists to look for it. They were skeptical, but they looked. And they found it, exactly where he predicted. This resonant state, the Hoyle state, is a nuclear doorway, held open by the precise tuning of the strong nuclear force. The energy of this resonance almost perfectly matches the thermal energy inside a red giant's core. The match is breathtakingly precise. If the resonance were just 4% higher, the reaction rate plummets. Stars would make 1,000,000 times less carbon. If it were 4% lower, the same thing happens. The window for carbon production nearly slams shut. Either way, the universe becomes carbon-poor. A carbon-poor universe is a silent one. No organic chemistry. No stable, rocky planets like Earth. No possibility for life. The stars would still shine, but they'd be factories with a broken machine. They couldn't forge the essential element. This isn't a minor adjustment. It's a star-level miracle. The strong force, one of the fundamental dials, is set to a value that creates this specific, life-enabling resonance in carbon-12. It feels intentional, as if the laws of physics looked ahead. They arranged themselves not just to allow stars to burn, but to allow stars to become creators. To turn simple hydrogen into the stuff of future worlds. This resonance is a signature, written into the heart of every carbon atom in your body, in every tree, in every diamond. It tells a story of a universe that doesn't just exist, but a universe that builds, and it raises a question. If the foundation of life hinges on such a precise nuclear accident, how many other accidents were necessary to get us here? That resonance in carbon, it feels like more than just a lucky break. It makes you step back and ask the biggest question. Why? Why does the universe seem so perfectly arranged for beings who can ask that question? This fine-tuning pushes us past physics. It brings us to a kind of philosophical crossroads, and there are 3 broad interpretations here. 3 different stories about reality. The first is the idea of a cosmic designer. The theistic interpretation. It says these precise settings aren't an accident. They are intentional. The universe appears finely tuned because it was tuned. For many, this points to a transcendent intelligence. A mind that set the laws and constants with a purpose. The argument is one of inference. If you found a pocket watch in a field, you wouldn't think it assembled itself from the dirt by chance. You'd infer a watchmaker. And proponents say the universe is infinitely more complex than any watch. So the appearance of design, they say, is evidence of a designer. It offers an answer that feels intuitive. It gives meaning to the cosmic story. But critics counter that this just replaces one mystery with another. Invoking a designer doesn't explain the designer's own origin. The second interpretation is the multiverse, the argument from sheer, staggering chance. In an infinite or near-infinite ensemble of universes, every possible set of physical laws gets realized somewhere. We naturally find ourselves in one of the very few universes that can support us. There's no design, no tuning, just a cosmic lottery with an infinite number of tickets, which makes our winning ticket inevitable. Physicist Leonard Susskind has championed this landscape view. He suggests it comes naturally from theories like string theory. It's a purely naturalistic answer. It dissolves the fine-tuning problem into a statistical inevitability. But the counterargument is its profound untestability. If these other universes are forever beyond our reach, is the multiverse a scientific theory, or is it a philosophical escape hatch? Some, like Roger Penrose, find the idea unsatisfying. They argue the specific order we see hints at a deeper, singular truth. The third path is the search for a final theory. The hope that the constants aren't freely adjustable dials, that they're mathematically necessary and unique. This is the dream of a complete theory of everything. In this view, the laws of physics could not have been otherwise. The strength of gravity, the mass of the electron, the resonance in carbon. These values are the only possible solutions to a single, elegant equation. There is no fine-tuning because there were no other options. The universe is as it must be. This idea has a powerful appeal. It promises a cosmos of ultimate coherence. But so far, no such theory has been found, and many physicists worry the mathematical landscape of possibilities might be vast, not singular, so we stand at this crossroads. Does the precise arrangement of the cosmos point to a purpose, a hidden hand guiding the numbers, or is it the ultimate selection effect, an illusion born from the simple fact that we are here to notice it? Or is there a beautiful, necessary logic waiting to be discovered? A logic that makes our universe the only possible one. This isn't just a question for physicists. It challenges our understanding of existence, of knowledge, of our place within it. It invites a personal reflection. When you look up at the stars, what do you see? A cosmos that whispers of intention, or one that shouts of infinite, indifferent chance? Or do you see a puzzle? A puzzle whose final piece will reveal a necessity so profound it redefines reality itself. The answer you lean toward may say less about the universe, and more about the kind of story you find most compelling. That crossroads between philosophy and physics is interesting, but it leaves a practical scientist with a different question. Can we test any of this? Is fine-tuning a real scientific hypothesis, or just a story we tell about the numbers? The scientific method needs evidence. It needs predictions we can check. So how do you test a universe that seems perfectly arranged? Researchers are trying in direct ways. One approach is to look for cracks. What if the constants aren't constant? Could gravity's strength or an electron's charge vary across space or over time? Finding that would shatter the idea of fixed dials. It would suggest the constants are more like environmental conditions. Maybe they change in different regions of a larger multiverse. Astronomers search for these drifts by looking at the most distant objects. Quasars, billions of light years away, act as cosmic beacons. Their light passes through ancient gas clouds, leaving a spectral fingerprint. By analyzing that fingerprint with immense precision, scientists can check if the fine structure constant was different in the early universe. Some controversial studies have hinted at tiny variations. The results aren't conclusive. The search continues. It's a meticulous audit of reality's rulebook across cosmic time. Another frontier is the cosmic microwave background itself. That afterglow map might hold clues not just to our universe, but to others. In the chaos of inflation, could our bubble universe have collided with a neighboring one? Such a colossal event might have left a bruise, an unusual pattern or a cold spot on the microwave background. Teams have scoured data from satellites like Planck, looking for these statistical anomalies. Some curious features have been noted. None have risen to the level of definitive proof. It's like examining a vast, ancient canvas for a single brushstroke that doesn't belong. Then there's the empirical test of structure formation. This is where tools like the James Webb Space Telescope become revolutionary. By peering back to the cosmic dawn, observing the very first galaxies and stars, Webb is testing our fundamental models. How quickly did those first structures assemble? What were they made of? Their size, brightness, and distribution are a direct readout of the initial conditions. The conditions set by inflation and dark matter. If the galaxies appear too early or too massive, or in the wrong patterns, it could mean our understanding of the fine-tuned recipe is incomplete. It would force a revision of the ingredients or the cooking time. Each pristine galaxy image is a data point, testing whether the universe truly followed the narrow path we think it did. Yet the core challenge remains. Many fine-tuning arguments are built on counterfactuals, universes that don't exist. We can't rerun the cosmos with a different strength for the strong force and see what happens. This leads some critics to argue that fine-tuning is a philosophical observation, not a scientific one. It identifies a remarkable fact, but without a testable mechanism, it can't be a hypothesis in the traditional sense. But this doesn't end the inquiry, it redirects it. The ultimate scientific response to fine-tuning is the pursuit of a deeper, more fundamental theory. A theory that doesn't have dials to adjust. A theory of everything that would derive the constants from first principles, showing they are the only logical outcome. In this view, the apparent fine-tuning is a clue. It's a signpost pointing toward a more elegant, unified layer of reality. The precise numbers are not arbitrary settings waiting for an explanation. They are invitations. They are the questions that the next great theory must answer. So the scientific journey transforms fine-tuning from a philosophical puzzle into a guiding principle. It tells physicists where to look, what problems are most profound. The mystery of the constants becomes the engine for discovery, pushing us to look deeper into the quantum vacuum, to build more powerful colliders, to conceive more beautiful mathematics. The universe appears tuned not to baffle us but to guide us toward understanding its true, inevitable nature. Mass comes from a field, an invisible field that's everywhere. The seventh tuned number is the vacuum expectation value of the Higgs field. You can picture the universe filled with this background energy, like a kind of cosmic molasses, and as fundamental particles move through it, they interact with that field. That interaction is what gives them mass. Without the Higgs field, electrons would just zip around at light speed. They'd never bind into atoms, quarks would be weightless, they'd never form protons or neutrons. The value of this field in empty space, its resting state, is a fixed number, and that number sets the masses for the W and Z bosons. Those are the particles that carry the weak nuclear force. So this one value becomes a master dial. It controls the strength of the weak force and the very structure of matter. If you turn that dial even a little, everything unravels. A slightly higher value would give the W and Z bosons much more mass. That would make the weak force incredibly feeble. And in the early universe, this force governs how protons and neutrons transform into each other. A weaker force would have thrown off the delicate balance of Big Bang nucleosynthesis. The universe might have ended up with almost no helium. And without that initial helium, later stars would struggle to ignite their heavier elements. The stellar furnaces would be inefficient. But a lower value for the Higgs field is even more catastrophic. It would make the weak force too strong. In the cores of stars, the process that turns hydrogen into helium relies on the weak force being just slow enough. It creates the bottleneck. That bottleneck lets stars burn for billions of years. If the weak force were stronger, that bottleneck vanishes. Stars would consume their hydrogen fuel in a frantic rush. They'd burn out in mere millions of years. Planetary systems would have no time to form. Life would have no cradle. And this same tuning also directly affects the proton-neutron mass difference we talked about earlier. That tiny imbalance which ensures stable hydrogen exists is tied to the Higgs value. Change one, and you change the other. So this single number, the resting value of an invisible field, doesn't just give particles weight. It calibrates the engine of stars. It guarantees the stability of atoms. It connects the quantum world to the fate of galaxies. Each finely tuned constant we've seen isn't an isolated dial. They're threads in a single, impossibly intricate tapestry. Tug on one, and the entire picture distorts. The Higgs value shows this interdependence with stunning clarity. It reveals a cosmos where every layer of reality, from the smallest particle to the largest star, is woven together. Woven by a common, precise, and breathtakingly delicate set of rules. These threads of interdependence, they point to something deeper. Maybe the cosmos isn't tuned for us. Maybe it's tuned for something more fundamental. There's a new idea, coming from physics and computer science. It says we should think of the universe not as a collection of things, but as a vast information processing system. In this view, space and time and matter, They aren't the primary reality, they are the hardware. The laws of physics are the operating system, and the constants, those finely tuned numbers, they are the system parameters. Optimized not for life, but for computational efficiency, for generating the most complexity, the most intricate patterns over time. Think of a simple computer simulation. One that models a snowflake growing. The program has a set of rules, a few lines of code for how water molecules bond. When you run it, you don't program every branch. The beautiful symmetry emerges from the interaction of those simple rules over many steps. The output is far more complex than the input. Now take that idea and scale it up completely. What if our universe is like that? A cosmic computation running on the fabric of reality itself. The laws, gravity, quantum mechanics, they are the algorithms. The constants are the key variables in the code, and the output of the computation. It's the unfolding history of everything, the formation of stars, the swirling of galaxies, the complex chemistry on planets. So fine-tuning in this view isn't a mystery about life. It's a requirement for a rich, long-running computation. A universe where the constants are set wrong. That's like a computer with a faulty processor. It crashes immediately, or it gets stuck in a loop, producing only simple, repetitive output. A void, or a quick flash and then nothing. Our universe's settings allow a computation that runs for billions of years, one that explores a vast landscape of possible states. It generates novelty. It builds structure upon structure. Stars and galaxies, then, are not the goal. They are emergent features. They are the naturally occurring patterns in a cosmos tuned to compute, to process information, to turn simple beginnings into a tapestry of extraordinary depth. Life and consciousness in this framework might be particularly sophisticated patterns. They arise when the computation reaches a certain level of complexity. We are not the purpose, we are a byproduct, a sign that the cosmic program is running a very deep calculation. This connects fine-tuning to computer science, to complexity theory. It asks, what set of physical laws maximizes the potential for interesting computation? Which parameters allow for the longest-running, most non-repetitive, most creatively complex processes? The answer might look a lot like our universe. With its balance between stability and change, its forces that allow for atoms and for stellar fusion, its expansion rate that gives both the time and the space for complexity to grow. This is speculative. It's far from a testable theory, but it offers a fresh lens. It reframes the question of apparent design. We are not looking at a watch made by a watchmaker. We might be looking at the output of a cosmic engine, tuned by mathematical necessity to generate the most interesting story it can. The universe appears tuned for structure because structure is what complex computation looks like. When it plays out across space and time, it turns the mystery of the constants into a search for the ultimate algorithm. The one rule, simple in its essence, that when iterated over cosmic scales, inevitably gives rise to galaxies and stars, and minds capable of wondering why. The search for cosmic order is an old idea. People looked up and sensed a harmony. The Pythagoreans in ancient Greece thought the planets moved in perfect ratios. They called it the music of the spheres, a universe tuned by geometry, a symphony only the soul could hear. It wasn't science, not as we know it, it was a poetic feeling. A sense the cosmos was arranged by a beautiful, intelligible plan. That idea changed over time. In medieval Europe, it became the great chain of being. A hierarchy from God down through angels, humans, animals, plants, to minerals. Everything had its ordained place. The universe was a narrative of divine intent. Every leaf, every star reflected a grand order. Disorder was the aberration, not the rule. Then came the scientific revolution. Isaac Newton's clockwork universe replaced the spheres with gears and equations. Planets moved by a universal law of gravitation, not angelic guidance. This was a different order, impersonal, mechanical. The cosmos was a vast, predictable machine. Beautiful but silent. No inherent music, just the hum of matter in motion. The question of why the machine had these particular settings wasn't really asked. It was enough that it ran. The next shift was Charles Darwin. His theory of evolution introduced a powerful new idea: chance. The complexity of life, the fit of organisms to their environment, wasn't from a pre-written plan. It was the outcome of random variation, filtered by survival over immense time. The biological world was not designed, it evolved, a cosmos of trial and error. Order emerging from randomness through a simple, relentless algorithm. For a while, these pictures seemed separate. Physics dealt with the clockwork, the deterministic laws. Biology dealt with the historical, the contingent, the chancy. The universe was a lawful stage, and on it, the random drama of life played out. But the 20th century shattered that division. Discoveries in physics and cosmology forced a convergence. We found the clockwork itself, the very laws, depended on a set of exquisitely precise numbers. Numbers that seemed arbitrary, yet were perfectly calibrated. And we found the universe had a history, an evolution from a hot, dense beginning. The laws were fixed, but their consequences unfolded over time. Through processes that involved both necessity and chance, like the formation of galaxies, or the resonant production of carbon in stars. The modern fine-tuning argument comes from this synthesis. It stands where the Newtonian and Darwinian visions meet. It asks a question neither could have fully formulated alone. What if the laws themselves, the fixed settings of reality, are the result of a kind of cosmic selection? Or what if they point to a necessity deeper than chance? We're no longer just asking about the order we see within the universe. We're asking about the order of the universe's very rules. So when we ponder the precise strength of gravity or the exact mass of the electron, we're in a conversation that echoes across millennia. We traded the music of the spheres for the resonance of carbon nuclei. We replaced the great chain of being with the cosmic web of dark matter. But the core yearning is the same: to understand our place in a cosmos that seems, against all odds, strangely welcoming. Our tools changed, from philosophy to mathematics, from observation to particle colliders, but the mystery has only deepened, becoming more precise and more profound with every answer we find. That golden age of structure we're in now, it might not last forever. The thing that makes it possible, dark energy, is also what ends it. We're in a kind of cosmic spring. A short window where things flourish before a very long winter. If you look ahead trillions of years, that acceleration from dark energy just keeps stretching space faster and faster. Distant galaxies will disappear over the horizon. Their light gets stretched until we can't see it anymore. Our local group of galaxies will merge into one, but everything beyond that fades into blackness. Inside that isolated island, stars will keep forming and burning and dying, but the fuel runs out slowly. The last generation of stars flickers out. Planets drift in darkness. Black holes evaporate over incomprehensible lengths of time through Hawking radiation. And then, on a timeline so huge it dwarfs all of cosmic history so far, even the last black hole dissipates. What's left is a near-perfect vacuum, a cold, almost empty void, maximum entropy. No energy to harness, no structure can form, that's the heat death. The most likely final fate, based on what we know now. From that far future, the fine-tuning we see today doesn't look like a permanent feature. It looks temporary. Local, a fleeting bloom of complexity in what's otherwise a simple, silent cosmos. The universe was tuned for a story, but the story has an end. That precise balance that allowed galaxies and stars and life. It's not a stable equilibrium. It's a transient phase on the way to equilibrium. And that raises a haunting question. Is the fine-tuning just for us? Is this cosmic benevolence just a brief, necessary stage in a much longer story that's ultimately indifferent? Maybe we're not in a universe designed for eternity. Maybe it's designed for a specific moment, a moment where questions can be asked. Or maybe our perspective is too limited. Some speculative models say this might not be the only story. There's cosmological natural selection from physicist Lee Smolin. It suggests universes can reproduce through black holes. Each new universe inherits slightly tweaked constants from its parent. In that scenario, universes that make more black holes, which need stars, galaxies, fine-tuned conditions, they are more prolific. Over a vast multiverse, the laws would evolve toward ones that maximize black hole production. So the fine-tuning for stars and galaxies becomes an evolutionary adaptation. Not a miracle. Our universe's parameters aren't chosen, they're selected for. Other theories imagine a cyclic cosmos, endless cycles of expansion, contraction, and rebirth. In each new cycle, the constants might reshuffle or reset to the same values. In a model like that, our finely tuned epoch isn't a one-time event. It's a recurring act in an eternal play. The heat death isn't an end. It's a prelude to a new beginning. These are bold ideas, unproven. They stretch testability, but they share a common thread. They place our moment of fine-tuning inside a vastly larger time frame. They ask us to consider that the laws we measure might not be eternal commandments. They might be local bylaws, or temporary winning numbers in an endless cosmic lottery. Looking forward in time forces a shift. It makes our current era feel precious and strangely fragile. The conditions that let us exist aren't just spatially rare, like the multiverse suggests. They're also temporally rare. A golden age nestled between a formless beginning and a silent end. That adds a new layer to the mystery. We're not just asking why the universe is tuned for us. We're asking why it's tuned for us now. In this brief sliver of cosmic time when the lights are on, and there's an audience here to watch. Each number is a thread. Pull one and the whole thing comes apart. You could maybe ignore one coincidence. A universe might get lucky once, but this isn't one lucky break. It's a series of them. A chain of margins, all razor thin. The expansion rate had to be balanced. The density ripples had to be just the right size. The strong nuclear force needed a specific strength. The neutron needed its precise mass. The matter-antimatter asymmetry had to favor us by 1 part in a billion. The Higgs field value had to calibrate the stars. And a nuclear doorway in carbon had to be held open by a perfect resonance. These aren't minor adjustments. They're foundational settings, and they all point the same way. A universe that builds anything more than a thin, eternal haze needs more than one dial set right. It needs a whole control panel. The argument's power is in that conjunction. It's the cumulative weight. The staggering unlikelihood that so many independent parameters would all, by chance, land in the exact narrow windows. Windows that allow for galaxies, stars, planets, and life. That's the synthesized mystery. A cosmos that appears from its first moments curiously arranged for the possibility of structure, and eventually observers. It doesn't tell us why, it just shows us the what. With a breathtaking clarity, we're left standing before a cosmic puzzle. A puzzle of immense depth, with pieces that fit together too perfectly to ignore. The question it poses isn't merely scientific anymore. It becomes existential. What does it mean that we find ourselves in a universe so curiously welcoming? And where does that clue lead us next in our endless quest to understand our home? That chain of coincidences brings us here. We started with the quantum seeds of inflation, and we ended with the spirals of galaxies. And what we found was a universe that seems perfectly balanced. Every step depended on it, the first flash of light, the forging of carbon inside stars. It all required this deep, delicate harmony. The numbers had to be right. The timing had to be exact, and the result is what we see, a cosmos full of structure. Full of light, a cosmos that could eventually tell a story like ours, but the meaning of that fine-tuning is still a mystery. Does it point to a single, deeper law? A law that makes our universe the only one possible? Or does it suggest a multiverse? A place where every possible set of rules exists somewhere, and we just live in the version that allowed us to be here. Maybe the answer is something we can't even articulate yet, something beyond our current ideas. But this mystery isn't a stopping point, it's an invitation. To look deeper, to think broader, to keep investigating. Each star you see is proof of that cosmic precision. Every point of light is the final product of a chain of perfect conditions. 13 billion years long. So when you look up, let that sit for a moment. Think about the circumstances. They allowed for a universe of things, but also a universe of meaning. A universe that can think about itself. And we are part of